So, today I want to talk about math with funny numbers. Fermi numbers. Presumably numbers, right? Okay, so by this I mean, why do numbers work the way they work? You'll probably have, okay, cool. So let's start with what are the numbers that you guys think of when I say numbers?
0.
Computer scientists. Okay, good. Start counting at 0, right? And then you count, yeah? And you go like 1, 2, 3, 4, 5, 6, 7, 8, 9. And this was very convenient, right? It kind of ran out of space before I had to do something weird. So the weird thing is this. When you have a number like, say, 2,718, right? What do these things mean?
Multiples of 10.
Yeah, those are counting a multiple of 10, right? So this first one, 8, is counting
10 to the 0.
10 to the zeros. This one is counting 10 to the firsts. This one is counting 10 to the seconds. Yeah. Okay. You guys are bored by this? Yes? Maybe? Okay. Further question? Maybe let me see if I can turn your brain off for a bit. So, say here's a number, 27 and a third, right? Which should be, like this part should be easy, right? The 2 represents 2 groups of tens, right? So that's repping 2, 10 to the firsts. The 7's repping
7, 10 to the 0.
7, 10 to the zeros. Okay, and then what operation are you sticking those together with to get your 27?
Addition.
Yeah, you're kind of adding, right? You guys with that? Okay, how about these guys?
3 to the negative 1. 3 times 10 to the negative.
Okay,
first.
so that's 3 times 10 to the negative first, and the next one is then 3 times 10 to the negative second.
Well, I mean, really, it's just the 3 times 10 to the negative first for the entire sequence because it's 1/3. 1, 3, 3, 3, 3, 3, 3.
Oh, okay. So this whole object you could think about as 3 to the negative 1
So long as
power.
it's continuing as a point as 3, 3, 3, yeah.
Yeah. So, but I think you were right, actually. So you were right in that this was 3 times 10 to the negative 1. That's what that first 3 after the decimal point means. The next 3 after the decimal point does mean 300ths, right? You guys with that? And then it sounds like you're hitting your brain against the wall I wanted you to hit, which is as this continues, right? You're really adding these up, right? And so you've got 3 times 10 to the negative third, and then there's also 3 times 10 to the negative fourth, and 3 times 10 to the negative fifth, and 3 times 10 to the negative sixth, and all the way and all the way, all the way down, right? Did you just fall down a rabbit hole in your head? No. Well, that sucks. You should have. Because how many things are there here?
Potentially infinite.
Definitely infinite. You see that? There's one thing for each counting number as I go backwards in the negatives. So 27 and a third, right? 27 plus a third is apparently 2 times 10 to the first, obviously, plus 7 times 10 to the 0, plus 3 times 10 to the minus 1, plus 3 times 10 to the minus 2, and continuing forever. And somehow this is supposed to sum up to 27 and a third? But that's infinitely many positive things added together, right? You guys all see that? No, none of them are 0. Yeah, this is a weird thing, right? Let me, by example, show you that at least infinitely many things don't have to add up to infinity. There's a question about if they get small enough, fast enough, they can add up to a finite sum. This is kind of a Calc 2 thing, but I need it here. Yes, that would be the word convergence for those of us who are not, or who are in math classes. So let me show you with quarters, because that one's easy. So here's a square. I'm going to assume my square is 1 by 1. I'm going to cut it into quarters, right? And then I'm going to color each of the quarters some kind of different bit. So I'm going to color this one with green slashies, and I have enough colors, I think.
There's a bunch
I'm going to
of
color this one black. I'm going to color this one red. So now each of the colors has a quarter, right, so far? Then I'm going to go into that remaining quarter. I'm going to split that one into quarters. I'm going to color the top left one green. I'm going to color the bottom right one black. I'm going to color the, oh god, color the bottom left one red. And then, okay, so now the green represents a quarter and a 16th, right? You guys see that? So let me work with this one. So the black stuff thus far is a quarter and also a 16th. You guys see that? Okay, if I do that cutting again, right? And I color the bottom right one black, the bottom left one red, the top left one green. Okay. Then I've added how much to my black thing? Yeah, a fourth of a fourth of a fourth, right? So really we could think this is a fourth squared. And then my next one will be a 64th, right? You guys see, if I continue in this process, there will be infinitely many things in this series, right? You guys with me? I'm chunking this up. What's it all going to add up to? Yeah, so am I ever going to get outside the box? No, so it's definitely less than 1, right? And specifically, I think you can tell that the black stuff, the red stuff, and the green stuff are all the same size, right? You see that? And they each take up how much of this box?
Same amount.
Same amount. So there's 3 of them taking up one whole box, right? So those are a third. You guys see that? So this thing is actually a third. So this is kind of a funny way of writing a third, and well, it's not decimal, right?
Well, it's not exactly a third, is it?
It is exactly a third, yeah.
Because there's always extra space to cut the next one.
But that's not part of the third.
It's the infinite.
You have a third, you have a third, you have a third, and then you have a little bit.
Yeah, so there's always that little bit, right? But that little bit is always also cut. Okay, see that? So you could maybe argue to me that this one point up in the far right-hand corner is not in one of these 3 colors. But that's just a point, right? It's 0 wide by 0 tall.
Well, not if you keep cutting it down. I mean, it could be 0,000,000 times a billion 1, but it is a number. It doesn't exist.
No. So, I got it. So, this is a discussion I wanted to have. So, what I'm doing, right, is I'm continuing this process. That's what the ellipses mean, right? So, infinitely down, right, I've cut this thing. So, we could definitely argue that there is something left up in the right-hand corner. You guys see that? But how big is the thing that's left? Like, what is the area of what's left?
Not 0.
Definitely 0.
It's 1 over.
If it wasn't 0, right? Like, if it stuck out into this box a little bit. Okay, with me on that? Like, just suppose it sticks out in the box. So suppose, let me kind of draw this picture. So, suppose I have taken this and zoomed in very, very far on it, right? And I have some little bit that sticks out into the box. Like, I don't really want to use one of the colors I've used. Suppose the blue little bit is remaining. Right? Like there's some little blue bit up there that I never got to. You guys all with me on that? Okay, so there's some little blue chunk up there. And maybe my quarters are way down, like, quarters are miles and miles down there, right? But this part had some length, right? As did this guy. And as I keep cutting that side length of 1 into quarters, I will eventually achieve a cut that's smaller than this. You with me on that?
Yeah.
So if you suppose this little blue thing had some finite area, then this must be at least the square root of that area.
Sure.
And then it has some finite size, and as I cut into quarters, I can always get smaller than any finite size. So maybe I have a division that's in here, right? So I have this cut. It's like, okay, you cut this into quarters. Okay, see that? Really, I'm cutting these side lengths in half every time, but it doesn't matter. You with me? So, now, this little part of the blue box got allocated to the green one.
Yeah.
This one got allocated to the red one, and then, or sorry, red one, green one, and black one.
Yeah.
Then further, one of those ellipses is to cut this again.
Yeah.
See that?
Yeah.
So no matter how small I supposed that this blue box was, eventually I'll end up cutting it up and allocating it.
Yeah.
The only way I don't allocate it is if it's actually just the point at the end, which tells you that so far, like in the end of this sequence, right? And there isn't an and, right? So in this sequence, the only thing I haven't allocated into one of the 3 colors is that dot at the end. Okay, see that? And that dot is 0 wide and 0 tall. So it contributes 0 area to this whole thing.
So then how does the 1/3 get completed to equal 1?
Would you guys agree that if I had a box that was 1 by 1 that didn't include the edges, it would still be 1 by 1?
Yes.
Does that make sense?
Sure.
Like if I said the things inside this box as opposed to this box, right? So what I'm after is how much stuff did I lose by saying not including the edges, right? So this edge is 1 long, but how wide is it?
0.
Yeah, it's 0 wide. So it has total 0 area. You see that? So these guys aren't contributing anything. I may as well really just leave them out. And that leaves off that point that I'm worried about not having allocated. Does that kind of make sense? So you can either do this with the closed edges and think to yourself, well, the point that I haven't allocated has 0 area, so it doesn't matter where it went. Or you can say, well, what if I just discard all the edges to start with? They don't have any area anyway, so who cares?
But then wouldn't you still end up with that point at some point?
No, I'll never end up with a point because I'm cutting things into
Right.
quarters, right? And so yeah, I'm never going to get this 1 point up in the far corner is never going to get allocated. But anything left of it or down of it is going to get allocated to one of the 3 colors.
Infinity is stupid.
Infinity is weird. That's true. You guys good with this? Okay. So this is the kind of the idea of the base 10 number system that you work in normally, right? Why do you normally work in base 10?
This is easy to work with,
Grew up with it.
and we have 10 fingers.
Yeah, because you grew up with it because you had 10 fingers. And everybody before you who started counting also had, well, most of them had 10 fingers when they started counting, at the very least, right? So
Phoenicians, right? Phoenicians were also the Phoenicians. Who was all crazy with their base?
I think
16?
Babylonian had like a base 16.
Babylon.
there have been a number of different bases over the years through human civilization, and I claim that the only ones that you need to know about are number base 10. And I'm going to put this little decoration on here a lot today because I'm going to need to talk about making numbers in different bases. So base 10 is the usual. If you leave that off, most people will assume you're talking base 10. There's another one we're going to use a lot, or that at least we should think about occasionally, which is computers use binary. Why do computers use binary?
Because they see in ones and zeros.
Why do they see in ones and zeros though?
5 volts, no volts.
Yeah, computers really only have on and off, right? Like each little transistor is either on or off. There's no 10 fingers kind of given to them, right? So they only really have 2 fingers. That's that transistor being on or off. Guys with me on that? Okay, and then there's this other horrible one, which is not actually horrible. It just is kind of seeming weird.
Well, all of the other bases are usually used for engineering and architecture because they fit into triangles and circles better. That's what I heard a long time ago.
Somebody was pulling your leg.
Look, that it's easier to get like perfect different types of sizes and scales of triangles using base 16 than it is base 10.
No, base
Someone
16
was pulled
is,
in your
is
leg.
actually used more for binary.
So the reason you use base 16 is the same reason that you use base 10, more or less. What I mean by that is, the reason you use base 10 instead of doing this, right? Oops. Oh god, now I have an extra. Okay.
Do you have 10 fingers, Joe?
Let me forget this number of fingers thing. The reason you use a number instead of this, right? Like if you had a whole bunch of tallies, like I have no idea how many tallies I've made here now. So the reason you say 13 instead of Blick is what?
Because it's easier to see. It's like shorthand.
Yeah, it's just a shortening, right? This really has nothing at all to do with the world as given. It's really just a human perception thing. So you want a quick way to talk about this. And so you label that with this quantity 13. And this 13 should get a base 10 today. Because I'm saying that's a base 10 number. Which means that this spot represents 10s. And this spot represents 1s. You guys with me on that? So base 16 is the same thought. It's for shortening of numbers. Why don't we use base 10 to shorten binary numbers? Because it sucks to do that conversion, basically. Base 16 is just a much faster conversion. So instead of having to run this kind of processing intense subroutine to convert base 2 to base 10, I can do a much easier subroutine that converts base 2 to base 16 for the purposes of shortening. Yeah, it's got to do with the powers of stuff.
Yeah.
I'll show you the trick. Yeah, it's really because the powers of 2 go 2, 4, 8, 16, right? And the powers of 2 don't hit 10. If they hit 10, then we wouldn't need base 16 at all. Like if 10 was 2 to the third, we'd be good to go. We wouldn't need base 16. That kind of make sense? Okay. So this is kind of the why.